Have you ever picked up a rock and just wondered what's really going on inside? I mean, it's not just a boring lump of stone, right? It's like a tiny museum, absolutely jam-packed with these beautiful little crystals. But they hold their secrets pretty tight. So today, we're going to go on a little investigation and find out exactly how geologists get them to talk.
And yeah, that's really the big question, isn't it? When you have a mineral that's locked deep inside solid rock and it's so tiny you can't even see it, how on earth do you figure out what it is? You can't just pop it out and hold it in your hand. Well, the answer is actually really clever.
You basically turn the rock into a window. You cut a slice of it so incredibly thin. We're talking about 30 microns, which is way thinner than a single human hair, that suddenly light can pass right through minerals that used to be totally solid. And once that light gets in, the mineral has no choice but to start revealing its true identity. So welcome to the microscopic world of the thin section. You can think of this as our crime scene. And that little mystery mineral inside, well, that's our prime suspect. The main tool we're going to use for this job is called a petrographic microscope. It's specially built to work with something called polarized light, which is exactly what we need to start asking our mineral a series of questions. By just watching how the crystal messes with this light, we can piece together its identity, clue by clue.
Okay, so the very first question we ask our mineral is the most fundamental one of all. Can light even get through you in the first place? On one side, we have what are called opaque minerals. Light just can't muscle its way through them. So under the microscope, they're just black, all the time. Think of something like pyrite or magnetite. We can see their shape, sure, but that's about it. But on the other side, we have transparent minerals. They let light shine right through. If our mineral is one of those, our investigation can really begin.
All right, so light is passing through our mineral. We're in business. Now we've come to a really critical fork in the road. The next question is all about the mineral's internal crystal structure. Does light travel the same way through it, no matter which direction it's going? First up, some minerals are what we call isotropic. This just means light passes through them the same way it would through a simple glass marble. The properties are identical in every single direction, and that's because their atoms are arranged in this really uniform cubic structure. Everything is super orderly and predictable. So how do you spot one? Well, here's the big test. When we look at it through a special polarizing filter and rotate the microscope stage, an isotropic mineral goes dark, and it stays dark. You can turn it a full 360 degrees and nothing changes. It's just black. At that point, case closed for that mineral. But what if it doesn't stay dark? Well, then we've got an anisotropic mineral. And this is where things get really cool. Think about a piece of wood. It's way easier to split it along the grain than against it, right? Anisotropic minerals are kind of like that. Their internal structure isn't the same in all directions. So the properties of the light passing through, like its speed, actually change depending on the path it takes.
This difference in structure creates this absolutely stunning effect. As we rotate an anisotropic mineral, it literally looks like it's blinking at us. It goes completely dark, a position we call extinction, 4 separate times in one single 360-degree rotation. That blinking is the unmistakable signature of an anisotropic crystal. The fact that our mineral is anisotropic is huge. It unlocks a whole new set of clues we can use, starting with its color. Now, some minerals are just, well, colorless, like quartz. But a lot of them have a very distinctive natural color, like the classic brown of biotite or the green of hornblende. And that color is all about the mineral's chemistry, which absorbs certain wavelengths of light and lets others pass through to your eye. It's a great, simple clue to start with. But that color can do something incredible. In some of these anisotropic minerals, we see a property called pleochroism. Because their internal structure has a direction, a grain to it, they actually absorb light differently depending on how they're oriented. And the result, the mineral literally appears to change color as we spin it around.
So, for example, let's say we're looking at a crystal, and in this position, it's a nice, light, yellowish green. Pretty color. But the real magic happens when we start to rotate.
We rotate the stage just 90 degrees and bam! The same exact crystal now looks like a deep, dark bluish green. That dramatic shift, that's pleochroism in action. and it is an unbelievably powerful tool for identifying certain minerals. It's a dead giveaway.
We're in the home stretch now. For our final set of clues, we're going to look at the mineral's physical form, its shape, how much it pops, and the way it breaks.
A mineral's typical shape, or what we call its habit, tells you a story about its history. A euhedral crystal, one with those perfect geometric faces, it grew in wide open space. But one that's anhedral, all blobby and shapeless, well, that one was crammed in a tight spot, fighting its neighbors for room. Others are naturally long and skinny, like a prism, or needle-like, or flat like a little plate. Next, we look at something called relief. And this is really just a visual trick. It's how much a mineral seems to pop or stand out from whatever it's next to. This effect is directly tied to its refractive index, which is just a measure of how much that mineral bends light when light enters it. The more it bends the light, the bolder and more standoutish its borders will look. And this pop isn't just some vague feeling. We can actually estimate a number from it. By seeing how much the mineral's borders stand out, we can get a good idea of its refractive index, or RI. A mineral with super thick, dark borders has a really high relief, which means it has a very high RI. It's another key piece of the puzzle. Finally, and this one is huge, we look at cleavage. Now, this is not a random crack. Cleavage is a specific, predictable break that happens along flat planes inside the crystal where the atomic bonds are weakest. You can often see these as a set of perfectly parallel lines running right through the mineral.
And here's the most important part. The same mineral will always have the same cleavage. Every time. It's like a mineral's fingerprint. Amphiboles, for example, always break with angles of 60 and 120 degrees. Pyroxenes always break at almost perfect 90-degree angles. If you can figure out the cleavage, you are so close to knowing exactly what you're looking at.
So there you have it. We started with a simple question about a tiny speck inside a rock. And we journeyed through this amazing, hidden world of light and color and shape. By slicing it thin and letting light shine through, a mineral can't help but tell you its secrets. So the next time you see a rock, just remember, it's not just a stone, it's a gallery, and it's just waiting for the right light to show you what's inside.